No question about 1, right? 2, 3. What did you guys pick anyways?
Yeah.
Good job. 4, 5. That was easy, right? Right here. Okay. 6. Huh? This one? Why? Single nucleotide change. You're right, but which one is the accurate one? You know, it's cytosine deamination. You know, like if you look at number 3, right? Number 3 is changed from C2 to U. Yeah. No, A is the answer. Yeah.
Quick question.
Yeah.
What if it was like from G to like U or something like that?
Yeah, G to U is unlikely, it doesn't happen.
Or like
because
a different one.
Yeah, G to T
G to T.
or G to C, it is transversional.
G to T is transverse.
Yeah, transition is in the same. Purine to purine is transition. Purine to pyrimidine is transversional.
What about A to U?
A to U, same thing. That would be an A to U again. Yeah, so you'll be thinking of it that way. As long as purine to purine transition, purine to pyrimidine or vice versa. If it's within the same family, it's transition. If it's within the 2 different families, then it's transversion.
Transversion?
Yeah.
So what does it mean by cytosine deamination?
Okay, so if you remember cytosine, this is the shape of cytosine. We talked about nucleotides. See, the difference between cytosine and uracil is only one thing. Yeah. Okay. So this is uracil, and this would be cytosine. So deamination. So when you remove this nitrogen, that's deamination. That's what you get. Yeah. What's the difference? Everything is the same except. So this is the same, right? And here is the same. All this is the same. The only thing that's changed is 6 and 7, right? C, yeah. 6 and 7 is changed. Everything else is the same. 6 and 7 used to be in the normal, should be G, and then in hemophilia became C. C and G are 2 different groups, right? G is purine and C is pyrimidine. So what do you think? Transversion. Did you guys get this one?
Yeah.
That's step 1 question. So if you got that one, you're okay. What's the sequence?
From bottom to top.
So which one is the sequence?
D.
D. So A, C, T, and then all C's, and then T. Yeah, good job. Good job.
And from there,
Yeah,
what's the number 8?
number 8. You want me to explain? Okay. Okay. First of all, you should know that they're talking about a fragment of DNA or a section of DNA that has normal restriction sites. You see, this is the normal restriction site. That means here, restriction enzyme, which is usually, if this is, I know the one that's in E. coli, EcoR1. Okay, so in E. coli, restriction enzyme 1. Restriction enzyme can only cut DNA at restriction sites. Good? Restriction sites are these unstable site where the restriction enzyme can recognize and attach and cut the DNA into fragments. What kind of enzyme is restriction enzyme, first of all? Endonuclease. So endonuclease, for example, are only able to cut DNA within, not from each end. So you will get fragment of DNA. If you get a huge, for example, this is a line of DNA. If you cut it, you'll cut it here, you cut it here, you'll get 3 fragments. A, B, C, of different lengths. Okay? So now, you have normal restriction enzyme. That means if you take this huge chromosome, and normally you'll only get 1 fragment. Normally you should supposed to get how many fragments? 1. And how long should this fragment be? 10 nucleotide kilobase. Is it kilobase? Yeah. 10 nucleotide kilobase long. That's a normal person. So what are they talking about in this case? Is the person homozygous dominant, recessive? What is it?
He's a carrier.
Okay, a carrier should, a carrier should have 1 copy that is normal and 1 copy that is abnormal. Correct?
Yes.
That's what a carrier should have. So if a carrier has a normal copy, the normal look, here it's telling you restriction sites created by who? By mutation. Normal copy shouldn't have them. Normal copy will be only 1 copy and you will get a fragment of 10 kilobase pair long. That's it. 1 fragment. So for a normal person, you should have that. A carrier should have 1 normal copy. So 1 fragment, that will be normal. So anything that has 10 is good. So this is good, this is good, this is good. So automatically I'm going to cancel these 2 out because they don't have the fragment 10. They don't have the normal copy. Plus, now the mutated copy should have, it should be cut here and here. At the end you will get 1, 2, 3 fragments. So the mutated copy should give you a fragment that is 2 kilobase pair, 3, and 5. Oh, I'm going the wrong way. So at the end you should have 2, 3, 5, and 10 fragments of DNA in this carrier person. Okay, and the only one that is E. Make sense? It simply tells you, like, if you take a sequence of DNA fragment and there are restriction sites created by mutation, that means you'll be able to cut them with restriction enzyme. So they'll look different. Their DNA will look different than a healthy person, or homozygous dominant, or homozygous recessive.
Can the question be in a different way?
Yeah.
Something else.
Yeah, I can say what's the I can say what would be the band seen for homozygous recessive or diseased person. For diseased person you'll only see 2, 3, 5. What would be the band seen for a homozygous dominant person?
Just 10.
Just 10. Yeah. Just 1 10. 1, 2, 10 doesn't matter, but 10. Okay. Make sense? Yeah. Okay. Any other question? No 10? No 11? No 12? No 13? 14 you said. Okay. A 21-year-old college student presents with dry cough. Dry cough. Ignore it for now, okay? Because you're not about clinicals right now. Low-grade fever and low energy. He is started on tetracycline treatment. So obviously he had infection. It seems to me like, just in general, if somebody has dry cough, lack of energy, and what else? Low-grade fever. What do you think? It is infection, yeah. What kind of infection? Bacterial, viral, typically viral, dry cough. So what is the infection if you have cough? Either pneumonia or bronchitis. So this is pneumonia, typical case of pneumonia in you guys, in college students. It's caused by mycoplasma. Give you this boring fever, muscle pain and ache, and you don't want to get up. And then mild, constant, boring, annoying fever, no night sweats and chills. That's always mycoplasma. But anyways, you don't know that, that's okay. So as long as, now if you use tetracycline, you should know immediately this is bacterial, because you don't use tetracycline for viral. At least the question is telling you that. Which of the following mechanism of action of this drug? So what is this? What are the mechanism of this drug? What does it do?
tRNA transfers from binding to the A site and a lot inhibits.
Okay, that's good. Let's start with something simple. Let's start with something simple. Does it inhibit tRNA? Does it inhibit ribosome? Does it bind to the ribosomes? Does it inhibit to RNA? Does it inhibit to tRNA? Which ribosomes?
40S.
30S, 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 30S. 30S is only found in bacteria. So if you treat bacteria, or if you treat a person who has bacterial infection, that means bacteria will not be able to reproduce itself. Tetracycline will inhibit only bacterial ribosomes. It should not inhibit human ribosomes. Correct? Because human ribosomes are what? 60S and 40S. Okay, so if the question is asking what is the mechanism of this drug, you will say 30S inhibitor or blocker. But here it's asking you what is the mechanism of action of this drug. Which of the following mechanism of action of this drug would most likely exacerbate, make it worse, the symptoms of this person, which is low energy feeling of low energy. So what mechanism of this drug? They're not talking about what mechanism the drug will actually kill bacteria. It's talking about how would it affect you. How would it make your symptoms of lack of energy worse? What organelle produces energy? Mitochondria. So if you didn't know that, you could choose it. That's one way. In addition to that, we talked about all ribosome inhibitors have the tendency to block bacterial ribosomes and human ribosome that looks like bacterial, and that's only mitochondrial. See, mitochondria looks just like bacteria. If you remember that, I discussed this with you. So because there are mitochondrial ribosomes in DNA, they look like bacteria. So these antibiotics could actually affect the mitochondrial ribosomes as well.
But this is not the mechanism of action.
It is a mechanism of action.
The result.
No. It is mechanism of action. Mean how? For example, if you say hi to me, how do you say hi to me? The result is good gesture, but the mechanism is the way you said hi. You can shake my hand, you can give me a hug, you can say, hey, how you doing? At the end, it's the same. Mechanism of action is the way it does things. Okay, so if you just focus on the term mechanism of action is not only inhibiting ribosomes in bacteria. Anything else could be mechanism of action, but it's not that prominent.
Instead of acting on because it says low energy, instead of acting
Okay.
on the right.
Clear or anything else? Okay, so it's talking about the patient's feeling. Is it making the patient's symptoms worse? If it does, how? It's supposed to make it better, but it has a side effect because it can block bacterial ribosomes and human ribosomes. And here they're talking most likely exacerbate the feeling of low energy in this patient. It's not talking about how would it make this patient better. If it's talking about how it would make this patient better, you say, okay, it blocks 30S ribosomes in bacteria, therefore bacteria will unlikely be able to cause infection, they die and whatever. But that's not what they're asking. How is it making the feeling of fatigue worse? This medication is supposed to get rid of that feeling, right?
Yeah, but if there is no synthesis of protein in the bacteria, so it's
Then
feeling
there
it.
should be no feeling of low energy, but now it's telling you why is it making it worse. See, I'm not asking about how is it making your feeling of low energy less, or how is it solving that problem. How is it making this problem worse, which is a side effect of medication. So again, in this case, the drug is causing a side effect. The drug is causing a side effect in this human being. Even though you treat him with antibiotic, your intention was to treat him with what? Antibiotic to get rid of the infection. But at the same time, there is no medication that has no side effects. So what I'm telling you, what is the cause of the side effect? The cause of the side effect is not killing bacteria. Bacteria is a good thing to kill, but now it's actually blocking your mitochondria. No. 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 Okay. If you didn't know what this meant, maybe that's why.
I didn't know what that meant. I should have looked it up, but I thought.
Yeah, it's simply making worse. Making worse.
Feeling the low energy. Now it makes, even if that was it.
Yeah, but some people can read it like, how is it going to resolve the low energy? How is it going to make it better? But this means making it worse.
we understood it like the mechanism of action of tetracycline on this bacteria.
No.
This is
You understood it
how
wrong.
yeah.
You understood it wrong.
Inshallah.
Okay. Are we good?
Yeah.
Yeah, B. Let me guess what you guys picked. C? Yeah. I think there was another distractor. Let me see, there was one more
We
distractor.
should know you by now, Dr. Valeri. There are 20 questions, right? Just one word, flip everything around.
That's right.
Yeah, I'm trying to prepare for that AMA's exam. I wish they give me the authority to submit all questions. See, the questions are, a lot of questions come from Northwestern, from UCLA, from John Hopkins, from Stanford. They're a group of questions that come from schools from India, schools from Pakistan, schools from Russia. But they're not majority. Almost 90% of the questions come from within the United States and Canada. Of course, Canada submits a lot. You know, at the end of the day, these are physicians. Some of them are good. You know, they're happy people. They're like, you know, this is make more sense. Some of them are just grumpy people. But then there's a committee that has to choose these questions. So in the committee, so we can submit as many questions we want. They won't choose. You know, so as I said, you know, you have something ahead of you. This exam is extremely easy exam. If you feel easy about yourself, just study the right way. Okay, just study the right way. But as I said, okay, there was one more question. I thought it was crazy, but let me see if you guys. Which one? This one?
Yes.
Okay. Anyways, what's the inheritance?
Excellent recessive.
Hemophilia is X-linked recessive. Very good. Okay, what's the most common type of hemophilia anyways? Classical or type A, right? I'll give you a bonus, raise your hand. What is the underlying cause of hemophilia? One. Okay, one hand. Anybody else? I'm gonna give you 2 points. That's 2, 3, 4. Okay, tell me first. If you get it, too bad then. Because he raised his hand first.
Factor 8 and 9 are missing.
I'm talking about hemophilia A, classical. You're correct. You give me 2 answers for both of them.
Factor 8.
Factor 8. What is factor 8?
It's a clotting factor.
It's a clotting factor. What does it do?
It starts to propagate the clotting cascade.
Good. So you put 2 extra points on your thing. Okay, so if you have extra, you can share one.
Send 1 point over.
Let me ask you this. What do you think you got on the exam? What do you think you got? No, give me the number. It's okay.
I got one wrong.
So you got 24 out of 25. Then share one with someone else.
Okay, you give it away though.
Okay. All right. So it's X-linked recessive, correct? Okay. We have to look for a pedigree that is X-linked recessive. Let's start with A. Now, just me looking at it, I'll go for D. Just me looking at it, without even knowing, because only male are affected, and normal parents are giving you affected children. And when the male has it, nobody has it. I don't even have to stress about it, just looking at it. But then I can analyze it just to give me that comfort, because we're all skeptical. We never trust anything, right? But if I was in the real exam, I'll just trust my guts and go with it. Don't waste time. Okay? But anyhow, let's go with A. Okay? In A, you have a female, has the disease. Male does not have the disease. If it's female and it has the disease, and then it's giving it to male and female, likely it's either it's dominant in this case, because each generation has it, right? In A, each generation, look, this generation, this generation, this generation. So at least it's dominant. If it's dominant, now we're thinking about it. If it's female, you know, if this was, so let's put dominant, but now we don't know if it's autosomal or X-linked. Is dominant okay? This is dominant, correct? Dominant, why? Because each generation has the disease. Each generation has the disease, at least one member. Now let's further talk about it. If female can give it to a female, if it's X-linked dominant, female can give it to a female, and female can give it to a male. Then, so far still okay. It can be X-linked or autosomal. But look right here. This man was able to give the X chromosome to his son. Impossible. Male-to-male transmission is not. That means she should be affected, and there should be a crazy non-disjunction to occur, which is impossible. Extremely rare. The fact is that she must have had 1 copy from mom, 1 copy from dad. Now, if it's X-linked, dad can only have the X chromosome, and the X chromosome can if it's given to daughter, the dad must express the disease. The dad is normal, so this is not X-linked. This is autosomal recessive. Let's go to E. In E, mom has a disease, and then son. Anyways, just look at it. It's every generation. If it's every generation, I'm going to think it's dominant. And then she gives it to one of her son, daughter, and one of her son. So that's 50% of her children has it. And then the son can give it to, this male can give it to female too. So it has to be autosomal dominant. This one is, of course, X-linked recessive. It's clear cut. Normal parents, the mom must be a carrier, and the dad must be normal. Therefore, all sons have to be normal. All daughters have to be normal. Because for daughters, that's not even a daughter. That's outsider. Daughters have to be normal because daughter can only get it if the dad has it in X-linked recessive, and only male have it from normal parents. So, Malcolm, good? You're good? Okay. 13? No? 14? We did. 15? How about 16? Why E? Only one that changes. Okay, that's good. 17? Why B? It says intron? Intron should not express itself, right? Where does it say intron? How do the sequence is intron? Data? That's what I'm saying.
Triple C, triple G, and then quadruple A.
Yeah, it's probably A till and then that's the one.
The fact that it doesn't express it, and symptoms are physical.
Yeah,
Stocko,
it just says that they don't express any symptoms of physical features. Second line.
I gotta read this. I think it's a mistake. I need a gene mutation discovered in a small population. Let's start with amino acids. Okay. You should have memorized amino acids that are polar, non-polar, positively charged, negatively charged. Okay, those are important. Okay, just roughly speaking, it makes your life easier. If you don't know the shape of each amino acid, it's no big deal, as long as you know what they look like in rough idea. But the most important thing, you have to know the shape of an amino acid in general. In a group, you should have a acidic group, a hydrogen, and R group. You have to know the general structure of amino acid. You have to know the general structure of amino acid. So let's start with some amino acid known as phenylalanine. As far as I know, phenylalanine it has a phenyl group. If a phenyl group is attached to, let's say, alanine, then it's phenylalanine. You know the shape of alanine, right? Alanine. I think we talked about it the other day. It has only one, the side chain or the group of that acid is only a methyl group. If you attach a phenyl group to that, it becomes phenylalanine. So alanine combining with the phenyl group becomes phenylalanine. But anyhow, so phenylalanine should look something like this. Something like that, yeah. Okay, now phenylalanine could be combined or hydroxylated, and it will be changed to, you know what, I guess I'll do that, that's fine. The first reaction of phenylalanine is, it is converted to tyrosine. Now the conversion to tyrosine is that you add OH. You add OH. You will add OH right here. Okay, so this is called hydroxylation. The OH group is known as hydroxyl group. I'm coloring with green. So what's the difference between phenylalanine and tyrosine? Yeah, phenylalanine hydroxyl is become tyrosine, that's all. Okay, you have this picture in your books, right? So phenylalanine can become tyrosine. Phenylalanine can become tyrosine.
Why did you draw that?
In what?
Phenylalanine.
Like, tell me.
I know organic and that doesn't make sense to me.
Okay, the phenyl group doesn't make sense to you.
No, that makes sense. The other,
Oh,
the vacuums.
this means a carbon. This means a carbon, and these means hydrogen. So I'm just lazy to draw, and I don't remember the exact molecules at each level. Okay, so let's put it this way. Yeah, it should be something like this.
Can tyrosine be converted to phenylalanine?
Which one?
Tyrosine.
Yeah, of course. Yeah. So amino acids should have an H, and they should have C, another C, and then O, and then O, and then they should have a hydrogen. And now at this position, if you add a phenyl group, this will become phenylalanine. But I don't want to draw this. You guys know the structure of the amino acid, so I don't want to go over it. Being lazy. Okay. All right. Now there should be an enzyme. There should be an enzyme that converts phenylalanine to tyrosine. Let's just do the diagram first. As soon as I tell you the diseases, it will make more sense. Okay. So now there should be an enzyme, and the enzyme should be named after phenylalanine hydroxylase. Why? Because you're hydroxylating which amino acid? Phenylalanine. If you're hydroxylating phenylalanine, then you should call it phenylalanine hydroxylase. That's the name of the enzyme at position 1. Now most of these enzymes, they require the vitamin B6. Vitamin B6. Vitamin B6. Okay. And they will usually also require tetrahydrobiopterin. So it requires vitamin B6, just remember that. Okay. So the enzyme is known as phenylalanine hydroxylase. Okay, so you have a beautiful picture. I spent like what, 10 minutes to drawing that for you guys, so use it. So the idea here is that simply phenylalanine is required to make tyrosine. Phenylalanine is required to make tyrosine. Now there's a term known as essential amino acid. What does that mean? Essential means the amino acid can become essential for you to get it from your diet because your body cannot make it anymore. So if this enzyme is deficient, phenylalanine hydroxylase, that means tyrosine becomes what? Essential. You cannot make it, you have to get it from your diet. Please understand what essential amino acid means. Essential amino acids are those which your body cannot produce. So you have to get it from diet. In this case, your body has the enzyme phenylalanine hydroxylase. So you should be able to convert phenylalanine to what? Tyrosine. Tyrosine is then converted to it's hydroxyl one more time. Okay. It's hydroxyl one more time. I mean, you guys should have a picture. I should have drawn one of them, but anyways, it'll be hydroxylated one more time at this position. So in red, it's hydroxyl one more time. Now the enzyme that should be number 2, enzyme number 2 should be tyrosine hydroxylase. Tyrosine hydroxylase. Tyrosine hydroxylase. Okay, tyrosine hydroxylase. Okay. Now, there's the thing. What should you call this enzyme number 2? Tyrosine hydroxylase. What should you call the product? Dopa. Why would you call it dopa?
Because there's two.
Dihydroxy. So D for, what is it? Dopa, right? So that's di. Oxy or hydroxy, O. P for phenylalanine. What's another name for tyrosine? Monohydroxy phenylalanine. If you add one OH, what's the name for OH? Hydroxyl group. OH is considered a hydroxyl group. So if you add one hydroxyl group to phenylalanine, you will call it monohydroxy phenylalanine. If you add 2, dihydroxy. If you add 3, trihydroxy. But as I said, we are lazy people. Maybe not you guys. I am lazy, and those scientists are lazy. So what they do, instead of calling it dihydroxyphenylalanine, it's too long. Let's call it DOPA. Okay, let's call it DOPA. This is one of the most important amino acid cycle you would need to know. I'm letting you know now. The most important one. Okay, so DOPA can then be converted to dopamine. I'll just put DA, dopamine. Dopamine. That means here is the carboxylic group. The carboxylic group here, it's removed by decarboxylase. DOPA decarboxylase. Enzyme number 3 should be DOPA decarboxylase, because you remove a carbon dioxide from DOPA, it becomes what? Dopamine. 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 And so now please remind me, write in your notes, I have to discuss, because I don't want to forget, I have to discuss in regards to the cycle, Parkinson's disease. I have to discuss pheochromocytoma, and I have to discuss neuroblastoma, okay, and I have to discuss PKU and alkaptonuria. That's how many conditions disease. So I have to discuss all of them. So we're going to spend some time on this cycle, so hopefully you know. Dopamine can further be converted to norepinephrine. And again, you do one more hydroxylation. So dopamine hydroxylase, enzyme number 4, dopamine hydroxylase will produce norepinephrine. Okay, norepinephrine is methylated, and I'll give you epinephrine. Okay, you have this picture in your book. You have it. Each one of you have it. So I'm going to erase it. I know you have it. I know you have it. And it's color coded. It's beautiful. So use it.
Dopamine gets hydroxylated?
Yeah. Use what you have already. So let me go back. This is phenylalanine. Okay. If you add one OH, it will become tyrosine. So this was phenylalanine, right? This is phenylalanine. If you hydroxyl phenylalanine, then it becomes what? Tyrosine, or monohydroxy phenylalanine. Same thing. So the first hydroxylation is done by phenylalanine hydroxylase, and you will get what? Tyrosine. Second OH, that second hydroxylation is done by tyrosine hydroxylase, and you'll get what? DOPA. DOPA. Are we good so far? Okay. DOPA could be converted to dopamine. Dopamine. If you decarboxylate DOPA, okay, if you decarboxylate DOPA, so that means this is no longer phenylalanine, this is DOPA, right? This is DOPA. If you decarboxylate, so that means carbon dioxide is removed from this position. Decarboxylase. So this should be DOPA decarboxylase. The enzyme here should be DOPA decarboxylase. And that gives you dopamine. That's great. Not a problem. Dopamine can be further hydroxylated. So now, the difference between DOPA and dopamine will be simply here. You should have OH, COO. For example, for DOPA. For dopamine, you don't have that. You'll okay. So it's in that sense. So dopamine. Now dopamine can be further hydroxylated, and that'll give you norepinephrine. And you have the structure. And norepinephrine can be further converted to epinephrine. Okay. So here you need an enzyme known as hydroxylase. Hydroxylase. I'm missing an X. And here is a methylase. Methylase enzyme. Okay, so this is not a problem. You're okay. But DOPA can also be converted to what? With the help of tyrosinase to what? Melanin. Okay, melanin. So there will be, again, I should have done it in a different way. Let's do it this way. it can be converted to melanin. And melanin does what? Gives you tanning. Okay, so now since you know this cycle, I'm gonna go over some diseases. So what do you need to know? First of all, you need to know that enzymes. The first enzyme is phenylalanine hydroxylase. Second one is tyrosine hydroxylase. Third one is dopa decarboxylase. Fourth one is dopamine hydroxylase. And then fifth one is norepinephrine methylase. Okay? Or methyl transfer. It transfers the methyl group into norepinephrine. The difference between epinephrine and norepinephrine is a methyl group. That's all, nothing else. So that's good. Now, it's okay for me to erase these guys, but I'm interested in these three. These three are very important. So dopamine, epinephrine, norepinephrine. They're known as catecholamine. Catecholamine. All three of them are known as what? Catecholamine. Okay, they're known as catecholamine. They're known as catecholamine. Okay, good. So dopamine, DA. Norepinephrine, epinephrine. These guys are known as catecholamine. Okay, these guys can be broken down further to vinyl mandelic acid or metanephrine. Why am I just having two P's? Metanephrine or metanorepinephrine. VMA is the most common one. All three of them. So norepinephrine will be metanorepinephrine. Epinephrine should be metanephrine. Okay. At the end, they're all converted to these products. And the enzyme here, I think in your book it's number 8. I see it, yeah. Number 8. Enzyme number 8 should be two of them. Catechol O methyl transferase. That's one. Or monoamine oxidase. Two enzymes, very, very important, because they do what? They decrease the concentration of norepinephrine, dopamine, and epinephrine. They break them down. That means metabolism. If you have too much epinephrine, you drink coffee, whatever, it somehow increases your nicotine and caffeine level. Okay. So these enzymes will get activated to decrease the concentration of epinephrine. We'll come to that. But know that, look, before that we talked about enzyme that produces catecholamine. Now we're talking about enzyme that will break down catecholamine, deactivate them, metabolize them, degrade them. Okay. The difference is monoamine oxidase. Monoamine oxidase is intracellular. COMT is extracellular. That's all. Okay. We're good so far, right? So let's go to some basic physiology of these catecholamines, and then it would help we can understand. So we have dopamine, we have norepinephrine, and we have epinephrine. Let's go to their sources. Where are they produced? See, dopamine is produced in the GI and nervous systems and some other cells as well. Especially we have to memorize a group of cells in the CNS that produce dopamine. A group of cells in the CNS that produce dopamine. And these cells are known as or neurons. So in this case, the cells are in the CNS are called what? Neurons. Neurons that produce norepinephrine dopamine is known as dopaminergic neuron. Dopaminergic neuron. Neurons or nerve cells that produce, again, this is a neurotransmitter. These three are neurotransmitters. Neurotransmitters are chemical messenger in the nervous system. You know, technically you have two type of systems that regulates your body. To regulate something, that means you have to send signals and messages, right? So similarly for you guys, if you want to regulate, you know, something, you call, you make phone calls, you communicate somehow. Chemical messengers are for communication between different cells. In the nervous system, chemical messengers are called neurotransmitters. Outside of the nervous system, they're called hormones or growth factors. Between white blood cells, they're known as interleukins. Anyhow, we'll get to that point. But for now, as long as you know something very simple, a nervous chemical messenger, a chemical within the nervous system that communicates between cells, it's known as neurotransmitter. You know, transmitters transmit what? Signals, right? So the neurotransmitter should be submitting what kind of signals? Because I'm transmitting some to you right now. Nervous signals. Very good. So they should be only released by who? Neurons. And they should act on what? Neurons. Are we good? That's what the definition of neurotransmitter is. Neurotransmitter. Released by neuron, acts on neurons. So if one neuron releases it, the second neuron will attach to it and then will activate the second one or inhibit it. I'll tell you how it works. But for now, just know that. So a name for epinephrine is also, it's also known as what? Adrenaline. Right? It's also known as adrenaline. Norepinephrine is also known as what? Noradrenaline. So the neuron that produces them are known as adrenergic neuron. Adrenergic neuron. Yeah. Adrenergic neurons. Even dopamine comes under the same category, but you know, it has its own selective name as well, dopaminergic neurons. Now we're gonna find out where are these neurons located primarily. They're located in multiple parts of the body, but okay. Dopaminergic neuron. Do you know where are they located? Substantia. Substantia. Okay. Now, where is substantia nigra located? Midbrain. Now, substantia nigra has two parts to it. Compacta and reticulata. Compacta and reticulata. Compacta is more compact, more dense, and it stains dark. Reticulata does not stain dark. And guess what gives you the dark color? Melanin. So melanin comes from all of these same things. So all of these can give you dark color. Okay. So it will be the compacta that produces it. Now midbrain is located where? So this is substantia nigra is located where? In midbrain. And midbrain is part of the brainstem. Good. Very good. So you should know that. Okay. Substantia nigra. So if I were to draw a cross section of the brainstem, or in this case, midbrain should look like this. And they should have this area known as crus cerebri. Next semester we're going to start with nervous system again, or CNS. And here is an area known as substantia nigra. I'll stain it dark. This area is what produces what? Dopamine. A lot of it, at least for the purpose of Parkinson's disease. Okay? Because in Parkinson's disease, so now let's go quickly, just let me tell you about it. In Parkinson's disease, there is destruction of dopaminergic neuron in substantia nigra. That's what Parkinson is. In Parkinson's disease, there is destruction of dopaminergic neurons within midbrain or substantia nigra. And we're done. So that means there's lack of dopamine. And as a result, dopamine is required for increased movement, increasing the intensity of movement, controlling movement. Without dopamine, movement is uncontrolled and it's sluggish. Okay, so I'll come back to Parkinson's, but for now, is it okay? Know that where is dopamine produced? Primarily in substantia nigra. Also in GI, you have dopamine produced as well. Okay, in kidneys, dopamine can be produced, but at small concentration, they have different function. Okay, so let's go to this adrenergic neuron. Yeah.
You just said that, substantia nigra compacta, looks dark. The presence of dopamine or melanin?
No, dopamine. But dopamine, remember, dopamine, melanin, they have the same structure, very similar. So all these guys will also give you slightly tan color. but because they don't stay in your skin, so you don't see it. But if dopamine accumulates in your skin, norepinephrine, epinephrine, your skin will turn dark as well. Melanin is part of the skin. Dopamine, norepinephrine, epinephrine is part of the nervous system in a small concentration compared to melanin. But they share the same backbone, which is tyrosine. All of them come from tyrosine. So they all have the ability to absorb light and not reflect. Whenever you absorb, you don't reflect, it will appear dark skin.
So substantia nigra has melanin too?
Not melanin. See, the thing is, now you're focused on this. Melanin is, see, tyrosine is a precursor for what? Melanin, dopamine, epinephrine, norepinephrine. Do they look alike? Of course they look alike. The dark color actually comes from tyrosine backbone. But melanin is a modified version of tyrosine that can absorb a lot of light. So you have a lot of melanin in the skin, for example. Norepinephrine, dopamine, and epinephrine is not found in the skin. But if it accumulates, it will also give you tan color. So they're the same thing, but just have slightly different structures. It's like all twin brothers, 4 or 5 of them. Slightly different. So no, you don't have melanin in substantia nigra. It's not needed. The dark color comes from dopamine, not from melanin in substantia nigra. But in the skin, it doesn't come from dopamine, it comes from melanin. Good? Yeah. Okay. Adrenergic neuron. Another way you can think about it, if you think about it, dopamine will look like a circle, norepinephrine like a square, and this one will look like a triangle. They're all very similar in shape. One hydroxyl group is different. Yeah.
Isn't that why if you have like a deficiency in melanocytes, you pretty much also have a deficiency in neurons because they come from the same base?
Okay. Now, norepinephrine is primarily produced in adrenergic neuron. Where would you find adrenergic neuron? See, one thing I want to tell you, norepinephrine has N in it, so it's primarily from the CNS. It's primarily the neurons, adrenergic neuron of norepinephrine are found where? In the CNS. Okay. CNS. And the nuclei that produces norepinephrine in the CNS are known as locus coeruleus. I'll take my vengeance in this life or next. What movie is that? My name is Locus Coeruleus. There you go, somebody's thinking. Okay. Adrenergic neuron. Okay. Now, epinephrine is primarily produced by adrenal medulla. Adrenal medulla. Adrenal gland has to produce adrenaline. The two names have to match, right? Adrenaline, adrenal gland. Okay. Adrenal gland can produce epinephrine and norepinephrine. But guess what? 90% of its production is epinephrine and only 10%, roughly speaking, is norepinephrine. And the CNS is primarily norepinephrine, small amount of epinephrine. Okay, if any. So adrenal medulla, which is on top of each kidney, right? Adrenal gland on top of each kidney. So if this is a kidney, and then on top of this you have an organ sitting around. And the core of this organ is known as medulla. The surface is cortex. So it's the core of this gland that produces epinephrine. Okay, so please know, adrenergic neuron in the CNS that produce norepinephrine is known as locus. Locus, L-O-C-U, locus coeruleus, C-A-E-R, coeruleus, E-L-I-O-U-S, locus coeruleus. Okay, think so. And the neuron that produces epinephrine is adrenal medulla neurons. Okay, so know these. Now, we know their locations. Let's go to their functionality. What do we need these neurotransmitters for? Dopamine increases movement. it increases movement, and it coordinates movement. Voluntary movement, not involuntary, voluntary movement. Okay, so that's dopamine. But dopamine, you have it in other parts of the brain as well. We're not only talking about substantia nigra. In the frontal lobe, parietal lobes, you have a lot of dopamine neurons, but they have a function of wakefulness. Now, if people who have low dopamine, they will have depression. If they have too much dopamine, they can become psychotic. Let's leave that for now. So dopamine is for movement, but it can also be used for increased dopamine can increase the risk of psychosis. Low dopamine, decreased dopamine will cause depression. In depression, dopamine is decreased, norepinephrine is decreased, and serotonin, all three of them. Yeah.
It is for when we have so much neighbors.
Yeah.
Blood doesn't necessarily
So you don't break them, and it will increase. Very good. So we will talk about, for example, depression, Parkinson's, and all those things that are related to this, so we can make sense out of it. But for now, so let's go to epinephrine and norepinephrine. They have similar function. So as long as you memorize one of them, it's good enough. They causes the condition known as, or the mnemonic of, flight or fight mechanism. That's what they do. Flight or fight mechanism. Flight or fight mechanism. So if you have epinephrine or epinephrine, it will make you fight or run away. And again, all of you know that, so I'm going to go over it in 2 minutes. I don't have much time. Quickly. The flight or fight mechanism start from top to bottom. Let's say brain, eyes. What else after eyes? Okay. Let's say mouth, and then skin, heart, lungs or airways. Airways better. Airways. And then what do you have? Heart, airways, GI. And then what? Bladder. Okay, so here you go. Now, epinephrine, norepinephrine, it increases activity in the brain. So it arouses the brain. Arouses the brain. So you will have wakefulness. Now let's put it this way. If the function of these is to do the flight or fight mechanism, I'm not going to write everything, you would know it. Imagine you see something extremely scary. Extremely scary. Big creature from a huge planet far, far away, and suddenly comes in front of you. You only have technically two options. Fight or run. Fight if you can win. If you can win, fight it. If you can't win it, run. Ahmed is fast, he will run. So either fight it or run. You know you're going to make that decision, right? For that decision, do you need your brain? Yeah, so brain has to be aroused, wake. Now, if you want to fight, do you want to see who it is? Or you want to fight blind, like Bruce Lee? Not a good idea. You need to see. So your eyes have to, pupils have to dilate. Pupils have to dilate. Good. Now, if you want to run, same thing. You want to know where to go. You're not going to run into a wall. So nonetheless, you need to see. So your pupils will dilate. Brain will be active. Wakefulness. Insomnia and things like that. If you have too much, it will cause insomnia, lack of sleep. So wakefulness. Focus. Concentration. All of those things are what happened with epinephrine or epinephrine. Eyes will dilate. Mouth. At this point, do you need to eat? No. So secretion, saliva should decrease. And that's what happens when you run. Suddenly when you run fast, what happens? Your mouth is dry. Yeah. Okay. Skin. Now, when you run, do you need to have more energy for your muscles to run? Yeah. If the muscles need more energy, brain needs more glucose. That means they're burning it at the same time. Burning produces what? Heat. So you have to release heat. So you have to sweat. So sweat glands will be activated by this system. So you will sweat. Okay? Now, heart. Do you think the heart has to pump harder and faster? It better, because now you have to provide energy to the brain and muscles. So heart rate will increase, heart contraction will increase. Let's move on to lungs, on airways. Now, in order for the heart to pump harder and faster, there's only one reason the heart has to do that, to deliver oxygen to your tissue. And the oxygen that the heart gets is from where? From lungs. So the airways have to dilate. The airways have to dilate. Bronchodilation should occur. Okay. GI. Now, when you want to run and you're afraid for your life, would you ever think of food?
No.
No, you better not. Because there's no running and fighting. You're just going to sit and be eaten rather than eating yourself. So, what the body does, it shunts blood away from the GI. So the GI will shut down temporarily. So it will vasoconstriction will occur in the GI, and all the blood should go towards muscles in the heart and brain. Because that's what you need. You need to think where to go, how to fight. You need your muscles to run or to fight. You need the heart to provide energy and oxygen for the rest. So GI will be shut. So there will be less secretion in the GI, less acidity in the GI, less mucus production in the GI, and GI will be decreased. Digestion will decrease. Now bladder. What happens when people get nervous? Yeah. See, the thing is, in this case, the bladder can increase contraction, the bladder can increase. Yeah. But the good thing is the sphincter of the bladder is made of alpha receptor, which is for epinephrine, which will stay closed. So, not in everybody's a bladder. So at this point, you don't think of peeing or anything. You just, the sphincter will close. Okay. So look for those things. So that's the function of this. Now, when we talk about these cycles, if any of these are affected, you will know what happens. Okay. Now, let's take a break. After the break, I'll talk about pheochromocytoma. I want to write it down, so you please write it down too. I don't want to forget. Pheochromocytoma. Cytoma. Neuroblastoma. Okay. Parkinson's disease, depression, psychosis, PKU, alkaptonuria. Okay. Anything else? Yeah, I think that should be okay. We'll talk about these conditions to see how they are related to this cycle. Okay. Alkaptone. A-L-K-A-P. Oh, there's a T missing. Alkaptonuria. Okay. So, take a quick break and we'll do that.